Hey, it's 10 after. It's time to start up. How's your day going?
It's going good and I'm excited for the weekend.
I understand that. I'm excited that I will, over the weekend, be able to rest and recover because, like, I'm on massive amounts of drugs for cold, and I'm feeling mostly okay. When I stand up, sometimes a little dizzy, but that's okay. I'm sitting down now. Um, I think it's always good to start with Q&A that's related to administrative things. And so why don't we dive right in? Any of you have questions about administrative matters, knowing full well that I've been sleeping a lot in the last day, and so maybe I didn't answer that email. I got across about 70 students in two classes. I got probably about 100 emails, so I probably didn't get to some of yours. But any questions?
I have a question. I don't know if it's quite administrative. It's more so homework related, but it's not like a specific question on the homework.
Yeah, yeah.
In the phrasing of the question 13, when asks us to use the formulas in the sections of the textbook, are we only supposed to use those formulas or can we use the JMP program?
Use GMP, and that's fine.
Okay.
Yeah, and I think that particular question has students ultimately making a comparison between two different statistical methods. One where you use a pooled T method, and I'm not so sure I really want you to do that. And so, if you felt like it was talking about a pooled T procedure, anything related to that, just don't worry about it. It's all good.
Okay, so I know that question D does ask for a pooled estimate.
Yeah, don't worry.
If we've already done, the problem with the pooled estimate, is it okay to keep it that way and just for
Oh
future
yeah,
problems?
yeah.
Okay,
It's
perfect.
it's never bad to have more in there. And the thing is, I will tell the grader, do not care. I don't care at all about whether the students do that pooled thing. Some students have done the pooled T before, and others will not have done the pooled T. And um, there is a slight benefit of the pooled T, but at a huge cost. A pooled T procedure does provide a slightly narrower confidence interval, okay, due to the higher degrees of freedom, but it's only valid if you're willing to assume that the two populations have identical population standard deviations. And that's not always the case. When the two populations have standard deviations that are much different from each other, the method we're encouraging you to use, the default built into JMP in most stat packages these days, is called Welch's method, or if you will, the T prime procedure. It's better than the pooled T, and so that's why we don't encourage the pooled.
Got it. Thank you so much.
Anyone else? Homework related, lab related, or other related questions?
I don't know if you already answered this, but is it based on completion or based on correctness?
Yeah, I will tell the grader. Actually, I talked to the grader earlier today, but I will, when sending the grader an email with the answer keys for the homework, I will say, okay, you grade as many problems as you feel you have time to grade within the number of hours you're allotted per week. And so I'll let the grader figure that one out. But grade a question or two, and then ask, do I have enough time to do another full question? Do I have enough time to do two full questions? And then grade until you're out of time, and then give points based on completeness for the rest of the assignment. So typically points would be awarded the following way. Question one, part A would be worth 0, 1, or 2 points. 0 means you didn't do it or is horribly wrong. 2 means it's largely correct. Maybe there's a little bit of fuzziness that's not perfect. And 1 is somewhere in between. And so maybe in one homework question with multiple parts, there'll be, 6 points there, and another 4 points for another question, 8 points somewhere else. And all of a sudden we're talking 18 points. And then the grader would say, well, of the total of perhaps 25, the other 7 would be for completeness. And then those scores will be entered into the grade book, and I will have inside the homework assignment, after you've uploaded your answers, that's where I'll put homework answers. So that way later when you want to refer to something, you'll have both what you turned in but also then the answers that I provide to the grader. The answers I give to the grader are considerably more detailed than the answers that I expect from you all, and I communicate that to the grader. But it's just, I put in extra stuff so that way students who might have one question or another almost always can find answers to their questions in the solutions I put online. Weston, you got a follow-up?
Slightly different. And if we don't have time for this, that's okay. But a content question about one of the homework questions.
Sure.
So for the grants Finch complete data question, it says do a 2-sample t-test on the data.
Yeah.
I do the fit y by x that I've done for all the others, and I go to that little red triangle, and it doesn't give me the t-test option like it does for the other things. So I was wondering.
I actually have a solution to this.
Yeah.
Great.
In the JMP software, I had to Google this actually. They sort the specific categories as a certain like kind of symbol type, and the symbol types in the program are actually the same, because years are considered continuous, but in the specific problem, it isn't continuous because it's only 2 years, so you have to change the symbol for years so it actually can graph, and then you can use the t-test.
Change it to ordinal or nominal?
Yes, exactly.
Yeah, I chose nominal.
Doesn't matter which? Nominal?
It really doesn't matter, but I would probably pick nominal.
Okay. Thank you. Much appreciated.
I think your question is, I'm seeing if I can find a data set where I've got a different collection of data sets open, but I'll find one and sort of highlight what you're talking about, because I think there's a real good point, and that is,
and that worked, by the way.
Oh yeah, it should, but I want to make sure everyone understands exactly what Bowie was saying. So I'm going to share a screen, and this is related to a data set that we're going to talk about in class today. So I'm like saving time even as we go. But here are data on the lifetime of various mice in a study on length of life, and then the treatment. You can see when I highlight treatment here, it sort of like shows treatment is highlighted down here in the columns, or lifetime, highlights lifetime. You can see that some of these things are like a blue triangle. Blue triangle corresponds to data that is numeric and continuous in nature. Usually our response variable will be continuous, okay, in its nature. This little red triangle-y thing, well, it looks maybe like a box plot, not a box plot, histogram. Yeah, good. You, for an explanatory variable in chapter 1 anyway, and in the t-test, you should probably have it as nominal. And so what Bowie was mentioning is that for the grants, the 2 different years in which these Finch were sampled, it might be shown as continuous as a number. If you see a blue triangle for your explanatory variable, but it's a t-test, you should have instead something that is nominal in its nature. Okay, so does that conform to what you were saying earlier, Bowie?
Yeah.
And then Weston, you're good with the way I followed up?
Yes, thank you so much.
Okay, anyone else on the software, perhaps, or something else? Okay, so what I want to do is to sort of dive in on new material today, and actually I've got it open already, and I think it's worth going slowly and having a thoughtful approach to chapter 1. It's really easy to sort of throw equations on the board, so to speak, or focus on something other than the conceptual. But I think focusing on the conceptual, and that's what we're doing in class today, plus the lab attached to today's class, is the way to understand it best. Okay? And so in a t-test, you want to see, is there a different mean between the 2 groups that you are comparing? Okay? What if you have more than two groups that you'd like to compare? Like I suggested earlier, there's this diet study on mice and measuring how long they live, the lifetime of the individual mouse, based on what it ate. The treatment was the food that they were assigned to eat. There are 6 different diets that were given to the mice, okay? And this was done in an experiment. I don't want to really stress experiment versus observational study. I'll just say this was an experiment. And so if if there is a difference in the population means, if that's what we conclude based on looking at the sample means and how close are they to each other, then you'd say, oh, well, the difference is either due to the treatment or it was just bad luck. And so the hypothesis test, we're really trying to assess the question, could it have been bad luck that might have caused us to see the differences we saw in our means? Okay. So if I were to show you these data graphically inside JMP, probably the best tool to utilize is Graph Builder. Graph Builder is your friend. Graph Builder will really try and help you tackle most any question you have. Usually I put the Y variable along the Y-axis and the X variable along the axis. Now, I'm sorry, I grabbed 2 things at once. Start over. Okay, just the lifetime goes here, and the treatment goes along the x-axis. And you can see these dot plots, dots where the data values are. And it looks as though maybe some of the groups have a lower mean than do some of the others. Okay. The question is it enough that you're convinced that there is a real difference in the group's means? Heck, if I turn on box plots, you could say, oh, is there a difference in the averages across groups? It looks as though maybe the box plots say at least the medians would seem to differ. But the method that we have in analysis of variance compares the means. Really, the 2 questions that we have are all of the means, the population means the same, or is there a difference enough between individual group means that we're convinced the population means are somehow different? Okay, null and alternative hypothesis. They're all the same. Null hypothesis, not all the same is the alternative. So in other words, at least 2 of the populations have different means. At least 2 of the diets have different average lengths of life that the mice have. Okay. So in analysis of variance, we're really gonna just compare our 2, not 2 means, but our 3 or 4 or 5 means to each other just to see if they are different. So a question might come up, why not just do a whole bunch of t-tests? Because we got these 6 different diets that we feed these mice. Couldn't we compare diet 1 to diet 2, diet 1 to 3, diet 1 to 4, 1 to 5, 2 to 3, 2 to 4, 2 to 5, 3 to 4? Okay, across 6 different diets, that's 15 separate t-tests I would need to do. And if I'm doing 15 separate t-tests, and well, what is the type 1 error rate? Back in that other class, that earlier stat class you took, you discussed a type 1 and type 2 error. Type 1 error means thinking that there's actually a difference between the groups when there really is no difference. That's something that could happen due to bad luck. We limited type 1 error rate to only 5%, but we've got 15 separate procedures, each of which has a 5% rate of type 1 error. It seems as though we would have a very huge type 1 error rate. It's likely across 6 different diets that we would see 2 different diets as appearing to be different, even if in fact none of them are. So we can't really just use a whole bunch of t-tests. Okay, so let's get into the nitty gritty. And I'm going to sort of go with a highlighting color to start. Our model here really is, and maybe I'm going to switch gears just a little bit so I can draw more effectively. Darn it. There. Okay, so our model over here is really that there's an individual data point, Yij, is equal to data point j from population I or receiving treatment I. So if there's 2 subscripts, I can completely describe every single data point. The first subscript corresponds to, hey, which group are you in? Second subscript corresponds to which data point are you in that group. And our model really says that Yij, the actual data point Yij, is mu, which depends on just which group you're in. Plus there's an error Ij. So an individual data point can differ from its group's average. So let's think about that. There may be an average length of life for a mouse receiving the low protein diet, but some mice live shorter than the average, so they would have a negative epsilon. Other mice live longer than average, so their error, their departure from the mean, if you will, the population mean, would be positive. So each individual data point is almost as though nature reaches into a bag of epsilons and says, okay, I'm going to grab an epsilon for you and add it to the average for the diet that you live, and that's how long you live as a mouse. Okay? Any questions about this conceptual box model? As you remember from that past stat class, lowercase Greek letters are things that you'll never, ever, ever really know. But Roman letters are things that you do get to know. So we do get to know the actual data point, how long each individual mouse lives. We don't get to know the length of life on average for its treatment or any individual mouse's departure from the population average. But we do have a hypothesis about about the population means mu's. And usually in a stat class, the null hypothesis corresponds to, yeah, they're the same. There's no difference. Nothing interesting here. For example, in a t-test, the null hypothesis is mu1 and mu2. They are the same. In a null hypothesis for analysis of variance across more than 2 groups, I would simply say across all k of the groups, mu1, mu2, mu3, all the way up through mu k, they are all identical, all the same, okay? So every single diet that these mice could be fed, they all have the same average length of life. And I guess that's possible. It's probably not the case, especially after you look at the graph of the data. It seems as though some of the groups have means that are higher or lower than the others, but we're not sure just yet. We just know our null hypothesis. A logical negation of the null is your alternative. At least one of the means is different from the others. Not all the same, at least one is different from the others. Next step, find a test statistic, and then a p-value, and then hit a conclusion. And I think the p-value, that will be sort of automated in this class, and the conclusion is going to be based on if the p-value less than 0.05, that's the typical level that we have for the test, we believe the alternative hypothesis. Otherwise, we stick with the null. That doesn't mean the null hypothesis is true. It just means that we have no reason yet to doubt the null hypothesis. Again, the null hypothesis is what we are promising we will believe until data convince us that it's wrong. And so the question comes to play, how will data convince us that it's wrong? That's where the test statistic comes into play. We have to come up with a way of measuring how close the sample means are to each other. Because if they're all close to each other or far apart, you know, we have to come up with a way of differentiating between those two circumstances. So let's dive a bit deeper in. Okay. Okay, there we go. Shoot, yeah, no. Okay, so inside JMP, the method we're going to use is just still fit y by x. And maybe I'll pull up the data one more time and we'll do that analysis. I'm going to kill that guy off here, but if I use analyze fit y by x, you're going to see that you could say, does the lifetime differ on average across the treatment levels? I click OK. You see before you get like dots in a plot. And it looks as though some of the groups are higher than the others, but we could, instead of, well, we don't see the T thing in front of us anymore. So GMP sort of says, okay, hold on. What is the nature of your data? You have an explanatory variable with more than 2 different levels. I can't do a t-test. I'm not even going to offer that to you. Do you want the means and then the ANOVA? And you can spot inside the analysis here a few things. One is it's a different looking analysis than before. There's this thing called R square, which we haven't fussed with yet. But we still do see something like a p-value. With a p-value very small, in this case, less than 0.0001, less than 1 in 10,000 chance, I would say there's less than a 1 in a 10,000 chance that the sample means would be this far away from each other if, in fact, the corresponding population means really were the same. Okay? And so it's going to be same thing as before, but we should probably dive into how the test statistic does the work. Okay, to understand the content in this class, we really need to sort of know how analysis of variance works. So I'm going to sort of start with what a couple of the assumptions or requirements are for analysis of variance. Okay, so let's maybe move the data off the side. So we talk about the assumptions and then the requirements. Okay, so one is that the distribution in each group is going to follow a normal curve. Two, each group has the same standard deviation. And three, there's independence between data points. Oh, that is horribly written, so let me just start over. And so what I mean by independence between data points, what I really mean is exactly and only one thing. If I tell you any one of the data points values, does that give you any information about any of the other values? If I tell you that in cage 316, the mouse named Bob, who was eating the low protein diet, had a lifespan of only 18 months, does that change how you would expect any of the other mice would live? Does knowing information about that mouse's length of life impact any of the other mice's lengths of life? If the answer is no, then you'd say you have independence. Okay, so we're going to require these 3 assumptions. Yeah, good. So any questions about the assumptions so far? Okay. So let's dive in on then the key player in analysis of variance. Okay, and every test statistic has a part which is, you'd say, oh, that's the central part in the test statistic. In the t-test, you remember y bar 1 minus y bar 2. We had that in the numerator over then the standard error for y bar 1 minus y bar 2. The key player here really was just the numerator. It measured how different the group means were from each other. Our friend SST in analysis of variance in ANOVA does the exact same thing. Okay, so let's talk about how SST is measuring how far the group means are away from each other in our data sets. Well, let's consider what would happen if every single group mean were the same. If all of the individual groups were identical on average. If every group mean, if y bar for group I is equal to y bar for group, well, shoot, 1, 2, all the way up through y bar for group 6. If they're all the same, then you'd expect one sort of an outcome versus if they're quite different from each other, you'd expect a different sort of an outcome. First thing to note is our friend y bar bar in our equation, y bar bar is equal to the grand mean, if you will. And that's equal to the average of all of the data points. Okay, so and so think if the group means were all the same, shouldn't they all be exactly at the grand mean? If the group means were always the same, if in every of the 6 diets, the mice lived exactly 22 months, wouldn't they average across all of the mice length of life be 22 months? So if the group means are all the same, the group mean minus the grand mean, that should be a difference of 0. And if I square 0, because the equation says we got to square that difference, and then just multiply by n the number of data points in the group, we will have SST being 0. If all of the group means are identical, SST will be the smallest possible value, 0. Okay, what if the alternative is true? What if individual groups are quite different, much higher or much lower than the average across all of them? Okay, if some of the groups have means which are really large or really small, I would imagine for at least that group, you would have this one minus the grand mean. That's going to be a very large difference. Or if it's considerably below the grand mean, that would be a very large and negative difference. Differences in the group means from each other will be reflected in a difference from the grand mean. And then if we square those and then multiply by the number of data points in each group, it's like waiting for the amount of, not waiting, W-A-I-T, W-E-I-G-H-T, waiting for the amount of data that we have in a particular group. What we see here really is if you have group means which are far away from the average across all the data points, that will be giving us a larger value for SST. Okay. So SST is tending to be small if the null is true, tends to be large if the alternative hypothesis is true. And like our t-test from last time, you're going to look at, okay, how far are the two means away from each other? We're dividing through by, I'll just call it stuff. Stuff with n's and s's, if you will, measures of spread in each group and number of data points from each group. The F ratio here is SST, our friend, divided through by, again, stuff that relates to n's and s's, measures of spread within each group, the standard deviation, and then n, the number of data points from each group. And then the other terms in there, K refers to the number of groups that we have. Okay. So let's get after how our ANOVA analysis of variance method works. In our textbook, we have as our word equation. You might say something like that the lifespan equals the diet. And that's not an actual equation, but in our textbook, we talk about in a word equation, we say that the lifespan depends on what the mouse eats. Okay, the diet has an impact on lifespan. So the left side of the equality is our response variable. What's on the right-hand side is the thing or things that could explain what's going on. Okay, so what we need to do is to sort of get into the nitty-gritty, and we're going to get to most of these in a later term, but let's get after our actually let's show you. Okay, so let's show you one more example first before we move too much further forward. Good time. And where is my there? Okay. 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 Here's another data set that you'll be using in one of the labs very soon. And it is data on discrimination against people based on the appearance of having a handicap. Okay. And the way the study was done was sort of interesting. They asked students at Ohio State University to participate in a study where they videotaped a job interview, and at the end of the interview, the students who watched the interview were asked to fill out a form. One of the questions in the form was, how qualified do you think this job candidate was for the job? The students all had a list of qualifications necessary for the job. And in the interview process, they're supposed to develop an opinion about highly qualified, 10, not well qualified at all, 0, like no qualifications, I guess would be 0. So a score has something to do with how well qualified you think that candidate is for the job. And this was an experiment, actually. The students didn't know it, but there was the exact same script followed by the exact same 2 actors for the entire job interview. And there were 1, 2, 3, 4, 5 different versions of the video shown. Okay. It was done 5 times. In one case, the actor playing the interviewee had no apparent handicap. In one, appeared to have an amputation. Okay, and so that's an amputee condition. In one of the job videos, the individual walked in using crutches. In one, there was a noticeable hearing aid in the right ear shown, and the people watching the videotape could see that there was the hearing aid in there. In one case, the person rolled in to the interview in a wheelchair. And so the only difference in the scripted interview was the way the person appeared. So you'd like to think that a person has going to be judged based on something other than their apparent physical capabilities, but rather, can they do the job? And this is a job which has nothing to do with any of these particular abilities. Okay, so the way we would tackle this question would be under Analyze, Fit Y by X, as before. Does the score given to a person on a job qualifications assessment based on a videotape job interview depend on the apparent handicap that they have in the interview? And here I see we have these are means that are all really pretty close. If I want to sort of fiddle with it a little bit, you can actually go ahead and under display options, you could choose to even show things like show me a line for each of the group's means. And you can see that the highest group mean and the lowest group mean maybe are a little apart, but it's not really obvious because there's a large amount of spread in each of these groups. There's a large spread. It's harder to see that there is a difference between the group averages. If we were to turn on our means in ANOVA procedure, you can see down with the p-value at the bottom, 0.0301. Yeah, there is a statistically noticeable difference between the group means. I think what we need to do is to come to terms with what this analysis of variance table does for us or gives us, okay? I told you earlier the sums of squares between the treatment groups, this 30.52 is our measure of how different the group means are from each other, but somehow the sums of squares between the handicap groups is converted into an F ratio, that's our test statistic, then ultimately a P value. Let's go down that path, okay? So our sums of squares in total in any analysis, and you can see sums of squares column, the total amount of variability, sums of squares total, in this case 203.4, is broken down into how much can be attributed to the handicap groups, in this case 30.5, and then other things, variability within the groups in this case. Sums of squares is a column, and there's 1, 2, 3 terms in it right now. And there's how much could be explained by the model we have, 30, and how much is the rest of it, 173, and how much is there in total. Okay. The question is, what fraction of the model, well, no, what fraction of the total variability are we explaining? And are we explaining enough that we say we're convinced there's a real pattern? Okay. So this is where we get into our friend, the ANOVA table. The ANOVA table is, well, I'd like to think about it like that physics class that you took in high school. And I'm going to sort of, I don't remember which one it was, but I remember there being a problem where, you had to take your lab of findings from, like a weight or something, and you recorded a lot of data. Then you did calculations on one whole page. And then you did another set of calculations on a second page, and a third and a fourth page. And each of those first 4 pages boil down to like one number that you circle down at the bottom. And then on that 5th page, you take those first 4 numbers and you put them together into an equation to get the outcome. This is what the ANOVA table is like. It's a set of accounting properties, okay? It's a set of accounting relationships that allows us to break apart our total variability, SSY, into what's due to our treatment variable, okay, across the different groups, and then error, and then hit a conclusion about whether there is a relationship or not, okay? So a couple of key facts that you should be aware of. One of them is degrees of freedom. There's a column entitled degrees of freedom. The degrees of freedom between the treatment groups, so DF column is degrees of freedom, between the treatment groups is always the number of groups minus 1. We have 5 different handicaps here. We've got 4 degrees of freedom for treatment. When we had 6 different diets that the mice had, we had, let's grab it and bring it over here. We had 5 degrees of freedom for across the treatment groups, okay? So there's degrees of freedom between the groups. That's going to be the number of groups minus 1. The number of data points minus 1 is the total degrees of freedom. So if we had 70 data points like we do here, 70 minus 1 would give us 69. That is the total degrees of freedom. And if I tell you a number plus something is 69, you sort of know the other one has to be 65. You can find it via subtraction. Not too hard to do. So we have our sums of squares total, okay? And we have a handicap, sums of squares, and then error sums of squares. If I tell you 2 numbers sum to 204, and one of them is 30.5, you know the other is 173.3. Our next step in our calculation of our test statistic is to determine the mean square, okay? And the mean square is always the sum of squares divided by degrees of freedom. So yeah, literally 30.52 over 4 is how we get our 7.6. Or 173.3 over 65 is how we get our mean square for error, mean square in the groups, if you will, okay? So that's how we're going to go ahead and get these terms. Last thing that we should be aware of is our F ratio. The F ratio is the ratio of mean square between the groups over mean square error. So MS between the groups over mean square M. Oh my gosh. Mean square error is that F ratio. And turns out that if the null hypothesis is true, both the numerator and the denominator of the F ratio, they tend to be the same. Numerically, we can show different class in this one. There's a proof for it. But numerically, we can show if the null hypothesis is in fact true, the mean square between the groups and the mean square within the groups, mean square between and mean square error, they are the same on average. And so that F ratio will tend to be about 1 if the null is true. So the F ratio tends to be close to 1 if the null is true. If I guess the null is not true, it won't be close to 1. It tends to be a bit larger than 1 if the alternative is true. And then the F ratio gives us a p-value. The p-value tells us exactly how likely is it we would see data like what we did see here if the null were true. That is easy to calculate. We're not focusing on how to do that by hand or with a table here. We just get a p-value, in this case 0.0301, and that allows us to say, we reject the null hypothesis because that p-value is below that 0.05 standard cutoff. We should believe instead the alternative hypothesis. We saw data that was surprising to us if the null were true. Surprising enough that we want to doubt the null hypothesis. We're not going to believe it anymore. This seems like a really good time to pause for questions because I notice y'all haven't been interrupting me so far in class today, but I really do like it when you do interrupt. So, hey, let's do some questions.
I'm a little bit confused on the I guess the terminology with the program in particular. So for example, the F ratio, T ratio stuff. Like I keep having to Google the difference between test statistic and that sort of stuff. Is there like a guide somewhere that we could maybe follow just to familiarize ourselves with those kind of terminologies so I don't have to Google it?
I think actually you won't really have a problem with that in just a second or just a day or so, because JMP always has the same looking output as every other stat package, but the p-value is always in JMP looking like that, probability greater than something, okay?
Got it, thank you.
And the F ratio is always our test statistic. And all this other stuff, I won't say it's unimportant, but it's the way you do the calculations to get to the F ratio. It's what if you were back in the 1930s and you had raw data, how would you create your F ratio test statistic? Part of the process was really, okay, I'm going to calculate and display for you each of these things. Okay, so the F ratio is your test statistic. The p-value is the way we hit our conclusion. The other bits are important to understand how they work because it will relate to other things we're going to do this term. But really, that's not the key feature. These are just steps along the way to calculating that F ratio test statistic. Does that get after your question?
Yeah, it helps a lot because I've been using the calculator and usually just kind of spits out the numbers without giving us all the nitty gritty. So it's taking me a little bit to get used to kind of reading the program.
Oh yeah, and that's the nice thing about going slowly, even though we're in a double-paced summer class. This is only review so far. Like every one of you are from a past stat class where you've already seen a t-test and an ANOVA and regression, what we're going to do next week as well. And so because of that, it's like, okay, we're getting used to the same things we knew how to do, but in this new context with this software package that we haven't utilized as much just yet. Anyone else? Okay. So what I'd like to do is to get after a little bit of notation sort of quickly. And this is notation that I'm not convinced you all need to really absorb in a sort of like I learn it by heart sort of way. But it's notation that allows you to say, okay, now I can understand these equations as I move forward into the future. So I want to highlight the various different terms that we're going to use in equations for our various different friends in the ANOVA table. So if K is just the number of treatments you have, so you think 5 different handicaps, K is 5. 6 different diets, K would be 6. N sub I is just the number of data points from the treatment level I. So if I told you I had 14 data points from each of the 6 different or 5 different diets, you'd say N1 is 14, N2 is 14, N3 is 14. Hey, let's actually bring our handicap back over here. You could see exactly that. Darn it, let's move it over here. And I can't. Okay, moving it over here so I could see it better. You could see in some of the output. Okay, you can see in some of the output you have 14 data points for each of the 1, 2, 3, 4, 5 different groups. So we have information about how many data points do you have in total, how many data points do you have from each group, how many groups do you have? Well, there's N, the total number of data points. That's in this case, it's going to be like 70 because I've got 5 different groups, each of which has 14. Yij, as we talked about before, has the data point J from group I. Yi bar is the average of group I. Si, let me remove the squared. Si is the standard deviation of group I, okay? And what we termed the grand mean earlier is just the average of all of the data points. So in this context here, we have now a way to sort of give you equations that you could then use perhaps to be moving forward if that is, well, if you have a problem where you need to sort of utilize equations, okay? So here is our equation for sums of squares due to the treatment. Okay, and this is one we showed you earlier, but we're going to take any individual group's mean, y bar for the group, compare it to the grand mean, take that difference and square it, and then multiply by n, okay? And that's sums of squares between the treatment groups. There's sums of squares total. That's the total amount of variability, and it looks sort of like a standard deviation equation, actually, if you think about it. Let's compare each individual data point to the mean of all of the data points and square that difference, and then we're just adding up across all the data points in a group, then all the groups. This is just finding out the total amount of spread between an individual data point and the grand mean, and it turns out that these first two, sums of squares total or treatment, plus SS error that we term, is sums of squares total. So it makes you think sums of squares error. Well, how do we sort of calculate that? That's a measure of spread of the data points within the groups that they are in. And an equation that I encourage you to think about is this one here. Literally, let's take the individual group's standard deviation and square it, multiply by the number of data points in a group, and just add those up. And so if there's very little spread within each of the groups, SS error will be small. If there's a lot of spread within the groups, SS error will tend to be large. But you could see here in our example, sums of squares, treatment plus error sums to the total. These are three equations for the 3 different terms. And I would say keeping track of them from the point of view of understanding conceptually what's being measured will be helpful for, darn it, Darn it. And what am I doing? Okay, good. Will be helpful for as we move towards an exam. Shoot, that's very early to be using that ugly word. But what I want to do is emphasize one thing, and that is if I were looking here at our set of equations, darn it, I've lost the ability to control this. Okay, so I can't erase that anymore, and I'm feeling frustrated, and it's also 5 o'clock. But let's just say usually is about 2 full class sessions to really grab onto analysis of variance. The thing is, hey, today we did the lecture bit. You're going to go and do some work with the lab activity between now and then, hopefully soon, because the lab is due on Monday. But I'd love y'all to sort of internalize it earlier than then, because on Monday we're going to do a little bit more work with analysis of variance that we can dot the I's and cross the T's and have a good sense of how it works and why it works. And then we'll be able to then use it as the stepping stone to regression as well. Okay, so that seems a good place to stop. What I want to do is to stop sharing screen and then stop the recording and